Welcome to this lecture series in linear algebra. In this lecture, we'll be looking at the second isomorphism theorem. And I don't want to recall anything because all we'll need is the first isomorphism theorem, and we've seen that ad nauseum. So these are the three problems for this lecture. And now let us get started. So it is going to be a short lecture. The statement of the second isomorphism theorem is that if U and W are subspaces of a vector space V, where we assume that all our vector spaces are finite dimensional unless otherwise mentioned, then this quotient, which is a legitimate quotient because, give me a second, there's a legitimate quotient because this contains that and this contains that. So both the quotients are legitimate. The second isomorphism theorem states that these two spaces are isomorphic. Even though we state it this way, what is more important is how they are isomorphic, not just that they are isomorphic somehow. I want to keep in mind the isomorphism. That is of more importance for general purposes. Anyway, so let's look at the proof. So what we'll do is we have this obvious inclusion map. So this map just takes little u to little u. And of course, this is a linear map. Here we factor out by w. And call it whatever, pi, let's say. So this is the natural projection map, which takes a vector v here to v plus w, the corresponding left coset. Okay, so we get a composite. This is our composite. Call it whatever, let's say t. So t is nothing but pi composed with this inclusion. And let's figure out what is the kernel of t. Okay, so kernel of t is those things in u such that pi of u is 0 in the quotient, which is same as saying, let me skip a step. Basically, it is all those things which are in w, because what gets killed under pi is precisely the elements of w. So the things in u which map inside w is precisely the kernel of this map t, which is nothing but u intersection w. So this factors injectively through u modulo u intersection w. We just applied the first isomorphism theorem. And we notice that this is an injection map. The hook arrow denotes injection. Simply because we applied the first isomorphism theorem, we quotiented out by the kernel of t, so we get an injection map. So if we can prove that this is surjective, then this would also be surjective and we would be done. Proving this surjectivity is actually very simple, because what is this map? This map is nothing but u going to u plus w. That's what this map is, right? So clearly this is surjective. You pick anything here. Okay, so maybe it's not completely clear, but an arbitrary vector in what color should I use? An arbitrary vector in this sky looks like u plus w, which is of course u plus w. So that's what makes clear that this is actually a surjection, and therefore this is also a surjection, and we have obtained an isomorphism between the correct quotients. That's it. That's the proof. We don't need to write anything. That is the power of diagrammatic proofs. It's very, very clear what's going on. Okay, so this has an immediate, very important corollary. So suppose u and w are again subspaces of a vector space V, then we have an equation about their dimensions. The dimension of the sum is dimension u plus dimension w minus the dimension of the intersection. And this is very, very analogous to the set theoretic equation, where if you have A and B finite sets, then the cardinality of the union is given in this fashion, and that's very, very similar to what we have up there. The proof of this is immediate from the previous proposition. The proof is we have u plus w modulo w is isomorphic to u modulo u intersection w, which implies dimension. Dimension of the two spaces must be equal, but the dimension of the left side is the difference of the participants. The difference of the dimension of the right side is the difference of the dimension of the participants. And if you rearrange this, if you just take this guy on the right side, you precisely get that, and that's it. So this is a very nice statement, very useful one, and you could have proven this directly. There is no need to go via this route, but I like to see it as a consequence of the second isomorphism theorem. A direct way, or maybe a more natural way to prove it, would be perhaps to, start with the basis of this guy, extend it to a basis of u and to a basis of w, and then you can show that the union of these two extensions is a basis of u plus w, and that way you can figure this out, which will look a lot like this, right? So that is one way, but I like this way. It's very much neater. All right, so as usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.